Hello everyone, my name is QuiCK. I'm part of the applied research team in iCloud. Today I'm excited to tell you about QuiCK, a queuing system we've built in CloudKit, the largest storage system in iCloud. We'll start with CloudKit and focus on tasks it performs asynchronously, without blocking client requests, which is essentially the reason for using a queuing system. I'll explain the motivation for building a queuing system that is integrated into the database rather than using an off-the-shelf one. Before presenting our solution, I'll briefly describe FoundationDB, the recorder, and CloudKit data model. Then, I'll present QZones, a new CloudKit construct that is used as a building block in our design. Finally, I'll describe QuiCK's high-level design, focusing on elements that were key for performance and scalability. CloudKit is Apple's cloud storage and application development framework that we presented at VLDB 3 years ago. It is used by the vast majority of Apple's apps and by thousands of third-party apps. CloudKit takes an extremely fine-grained approach to sharding. It maintains a separate logical database for each user or every app. For example, there is a separate logical database for the photos data of each user, and these databases have a common schema. CloudKit moves these logical databases across data centers to balance capacity and load. This approach allows for almost unlimited scale and provides enormous operational benefits. Overall, we maintain billions of logical databases. In many scenarios, CloudKit can respond to a client's request before it finishes taking all the actions required to process it. For example, let's say that I want to share this keynote with my team members. After my sharing request arrives to a CloudKit server, we modify access control metadata stored in my logical keynote database in CloudKit, enqueue an async task in a queuing system, and send a response to the client. When executed, the queued task will update the databases of my teammates, potentially in different data centers, to reflect that access was granted to a new keynote file. CloudKit servers at those locations also send notification to my teammates' devices. Upon receiving the notification, my teammates can access the shared file in my logical database and review my keynote presentation. In general, there are multiple benefits for deferring task execution. The obvious one is reducing client request latency. Asynchronous processing also reduces our services' dependence on other services, which improves the availability of our system. Dependent services may be temporarily offline or unreachable, while our service continues to serve clients. In addition, we can optimize the execution of asynchronous tasks, for example by batching, eliminating redundant tasks, and more. CloudKit enqueues multiple types of tasks. Some tasks might have relatively long processing duration, such as built-in indexes or cascading database updates. Other tasks might be relatively short, but require communication with other services. For example, push notifications require interaction with Apple's push notification service. Let's look again at the keynote sharing example. We saw that the first step was to modify the database. But what happens if we commit the database changes, return success to the client, and then fail to enqueue the task? Well, no one will know about my keynote. If we try to handle this scenario by first enqueuing the task and then committing the changes, then notification might be sent to my teammates, but the database commit might fail or just be really slow, so that when my teammates try to access the database, their request is denied. Here is another scenario. This time when deleting a directory in iCloud Drive. A user performs a delete operation, and CloudKit enqueues a deep delete task to the queuing system in data center 1. Now, CloudKit might decide to move that user to a different data center, in our example to data center 2. This means that when the queuing system in DC1 tries to execute the task, the corresponding database will no longer be there. Executing tasks remotely in this scenario might be problematic with respect to security and semantics, and explicitly tracking and validating users' tasks in addition to their data would significantly complicate the system. To summarize, the lack of transactionality between data and tasks can lead to undesirable effects and race conditions. Having the tasks stored in a separate system complicates data migration and state management. More generally, the external queuing system is oblivious to CloudKit's tenancy model. You can't query it to ask for user tasks or provide fair scheduling across tenants. In addition to that, maintaining a separate highly available queuing system has its costs in terms of provisioning, operating, tuning, as well as performance, especially if cross-data center replication is required. And so we decided to go with a different path than using an external queuing system. Our solution is QuiCK, a queuing system that is integrated in CloudKit. Let's see the keynote sharing scenario, this time with QuiCK. The first action modifies the data. Then, as part of the same transaction, a task is stored in the same database of that user. This task is not accessible to the user but only to QuiCK. Upon commit, CloudKit responds success to the user. After commit, QuiCK processes the task and notifies CloudKit servers responsible for the relevant databases, which in turn modify these databases and send notifications to my teammates' devices. Let's examine the benefits of having such an integrated queuing system. We now have the ability to store the data in the corresponding async task transactionally. After the task is processed, we can delete it from the database, which gives us at least one semantics. In cases where the task itself has no external side effects and only affects the database, we can combine its processing and deletion in a single transaction, which can provide exactly one semantics. Tasks are now stored close to the data, moved with the data, and treated like data. The queuing system is highly available because CloudKit itself is highly available. Having said that, it's important to add that there are some challenges of integrating a queuing system in a database. In fact, using an ACID database for queuing is sometimes considered an anti-pattern, mostly due to the potential hotspots and producer-consumer contention one needs to overcome to make it work. Of course, we needed to make sure that the system is scalable and resource efficient, but we also add an additional major challenge, which is beyond the scope of this talk. QuiCK is replacing an existing external queuing system, serving production traffic at scale. Before we go deeper into QuiCK, let's talk about the broader system and the database on which it relies. CloudKit relies on FoundationDB, an open source key value store which we are presenting in this year's SIGMOD, and on FoundationDB Record Layer, an open source database published in SIGMOD 19. At a high level, FoundationDB is a stateful storage tier, providing ordered key value storage and supporting strongly consistent multi-key transactions. For many more interesting details, please see the FoundationDB presentation. The record layer adds features one would normally expect from a database: transactional secondary indexing, schema management, query planning and execution, as well as advanced features such as support for massive multi-tenancy. The record layer is completely stateless and runs on CloudKit application servers. A client request can be served by any CloudKit application server that accesses the relevant data in FoundationDB. This design allows us to scale the storage and compute layers independently. On top of the record layer, CloudKit maintains logical databases for each user and app. Each logical database in CloudKit is divided into zones. Zones are a useful way to organize data. Each zone contains records. Records are the basic unit of storage. Each record is a dictionary of key value pairs called record fields. Fields can contain simple value types, for example strings, numbers, dates, or more complex types. CloudKit supports a range of APIs that allows changing records and zones, syncing data between devices, querying data, registering for a change notifications, and more. Unlike many other mobile backends, CloudKit supports schema evolution and validation, which helps app developers manage their data. Next, we'll tell you about a new type of zone we created in CloudKit, which exposes Q APIs rather than CRUD. This new type of zone is used directly by some CloudKit clients and is used as the basic building block in QuiCK's design. Each record in CloudKit has a record ID. In a queue zone, each record also has a vesting time and a lease ID. The vesting time is the time at which that record becomes visible for DQ and pick operations. This is useful for submitting items that need to be available at a later time rather than immediately. All records in the zone are sorted by their vesting time, using transactional secondary index defined in the FoundationDB record layer. For example, here's a pick operation trying to pick up to 4 vested items. Based on the vesting time, you can see that only 3 records are vested, given that the current time is 6. Therefore, the response consists of the record IDs of the 3 vested items. Vesting time is also used to implement leases. Here is how it works. In this example, we have a client requesting to obtain a lease on record 1 for 59 minutes. We update the record's vesting time to 59 minutes from now, which means 7 o'clock, and we assign a random lease ID that is stored in the record and is also returned to the caller. Notice that record 1 is not removed from the queue. Since the records are sorted by vesting time and only vested records are returned, record 1 is effectively hidden until 7 o'clock. At that time, the record automatically becomes available again, and the caller loses the lease, unless it actively extends it, for which it needs to present a valid lease ID. This is essentially a lightweight, fault-tolerant leasing mechanism. Picking or obtaining a lease on a record won't remove it from the queue. In order to actually remove a record, we have the complete operation. If the record is not vested, a matching lease UUID needs to be provided in the request, which essentially makes sure that the lease is held by the caller and not by some other client. And at last, in order to add records to the queue, we have the enqueue operation, in which we give the record that we wish to enqueue. Here we only mention the record ID field. And also the vesting delay, in this case 7 minutes. Success is returned once the record is added to the queue. In addition to the 4 operations that I presented, we also have dequeue, which is basically pick and obtain lease in the same transaction, extend lease that increases the vesting time, and requeue that releases the lease and updates the vesting time. Now, let's see how we leverage the queue zone abstraction to create an integrated queuing system. In this diagram, we have a single FoundationDB cluster. In it, we see a cluster DB, which is a special type of CloudKit logical database that we create in each FoundationDB cluster and use for managing our queuing system. In this database, we have a queue zone named QC that acts as an index to all other queue zones in this FoundationDB cluster. This cluster level queue allows us to find non-empty queues of CloudKit tenants stored in this cluster. When a client enqueues a task, it starts the transaction and enqueues the task to a queue zone that we store in the relevant database, here DB1, right next to the other data of this client. Next, we must ensure that this task can be found by QuiCK. To this end, a pointer must exist from QC to DB1. To check whether it already exists, we use a secondary pointer index in cluster_db. This index transactionally maintained in the record layer. In our case, the pointer is missing, so we have to create a new pointer. Finally, we enqueue a pointer to DB1 into QC. Note that all these operations happen in a single transaction. Let's consider another scenario, in which a pointer already exists in QC due to an earlier enqueue. Client 2 starts a transaction by enqueuing a task directly to queue DB3. Then, as part of the same transaction, it reads the entry in the pointer index. Since it's already there, it commits the transaction. After the commit, the client initiates a new transaction in which it reads and potentially updates the vesting time of the pointer. This can help reduce the processing latency, but it isn't required for correctness and we don't need to retry this transaction in case it aborts. Now let's see what's happening on the consumer side. We start with a scanner thread. We have one scanner in each consumer instance. The scanner is responsible for picking vested pointers from QC and passing them to queue managers. A queue manager receives one pointer and starts by obtaining a lease on the pointer. Then the queue manager dequeues several tasks from the corresponding queue and passes these leased tasks to workers. Taking a lease on the pointer is done so that different consumers trying to find work do not contend on individual tasks, but rather on pointers to whole queues of tasks. Taking a lease on the task level is done in order to prevent duplicate task execution, as we'll explain in the following slides. A worker receives a single task. It processes the task and then completes it, which removes it from the queue. Zooming out, CloudKit is deployed in many partitions. In each partition, there are multiple FoundationDB clusters. Each contains a single QC, a top-level queue of pointers. We also have multiple instances of consumers in each partition. Each executes the algorithm we just saw. As I mentioned, avoiding hotspots and contention is essential when integrating a queuing system in the database. Let's see how QuiCK tackles this issue. First, note that there is no contention on the low-level queues, since enqueue creates new records that aren't affected by consumers' actions. The only possible contention is the top-level pointer queue, on a specific pointer. Enqueuing an item normally involves reading the pointer index, and not the actual pointer record. This means that the pointer record is usually not part of the enqueue transaction read set, and therefore only pointer deletion, which also updates the pointer index, can collide with enqueues. Since deleting and creating pointers can create contention, we don't delete pointers right away when queues become empty. Instead, we use a lazy approach and a way to make sure that the queue remains empty for long enough and only then delete the pointer. However, when a queue becomes empty, we hide the corresponding pointer by setting it to vest in the future. This means that we avoid unnecessary deleting and creating pointers, as well as avoid wasting scanner cycles by repeatedly examining pointers to empty queues. Let's examine concurrency among consumers. Generally, consumers contend only on the top-level pointer queue. In order to reduce contention, scanners select random subset of vested pointers and pass their selection to queue managers. Using random selection means that in some rare cases, scanners might take a long time to get to pointers, which affects tail latency. To address the potential issue, one consumer is dynamically selected to pick pointers in order. How do we deal with tasks that require long execution time? We have several strategies. First, we limit the number of tasks of a certain type that can be executed concurrently. This bounds the resources QuiCK spends on long-running tasks and also help protect dependent systems that may be affected by a certain task type. We also set limits to the time each worker can spend on a given task. We make sure that long-running tasks in our system are walk-preserving, meaning that they can be killed and resumed without restarting the walk from scratch. Finally, we use heartbeats to prevent duplicate execution of tasks. A worker tracks the status of its tasks and periodically extends the list, which makes it unavailable to other workers. There are many more interesting details in the paper that we didn't cover here, and I encourage you to take a look. To summarize, we saw why it makes sense to integrate a queuing system in the database, whether for strong semantics or for having tasks treated as data, better availability, or for reducing external dependencies. We presented QuiCK, a queuing system that is integrated in CloudKit. It stores tasks alongside data, allocates resources fairly across CloudKit tenants, manages to reduce contention to a minimum, and relies on a new queue zone abstraction. Thank you very much.